Good morning, all. Welcome to this session on STAAD-Pro. So, in today's class, we are going to see how to design a singly reinforced beam in STAAD-Pro software. This problem, which we are going to see today, is the continuation of the theory class. And let's get into the problem. Design a simply supported beam for the following data: clear span 4.77 meters, wall thickness 230 mm, live load 10 kilonewton per meter, concrete grade M30, steel grade Fe415, and nominal cover 30 mm. We will just rush through the manual design and we'll take a few input from this manual design for STAAD-Pro. Geometry. So we have calculated the effective length as 5 meters, overall depth as 450 mm, uh, effective width as 250 mm. Load calculation and analysis. So we have calculated the total load on beam as 12.813 kilonewton per meter, and this problem has now been reduced to a simply supported beam with the uniformly distributed load. So resolving this simply supported beam, we have found out moment and shear. We have converted them into ultimate moment and ultimate shear force. So the value of ultimate moment is 61 kilonewton meter and ultimate shear force is 49 kilonewtons. And we had checked the adequacy of the section and found out that the section is under reinforced, so which will end up in a singly reinforced section. Then calculation of area of steel. So we have found out the area of steel required is 448 mm square, and we have arranged two number of 20 dia bars throughout the bottom, and steel provided is 628 mm square, and percentage of steel provided is 0.625. At, at the top we are providing minimum steel, so which calculates to two numbers of 16 dia bars at the top throughout the beam. Then check for shear. So we have found out tau v, which is 0.488 newton per mm square, and tau c was obtained from table 19 of 456. Tau c equal to 0.545 newton per mm square. So in this case, tau v is less than tau c, minimum shear reinforcement will be provided. Calculating the spacing of stirrups, assuming 8 mm uh, rod has been used and two-legged vertical stirrups. So the calculation comes out to 300 mm. So we'll be providing 8 mm two-legged vertical stirrups at 300 mm center to center. Then the output of the design was the drawing. So we had 220 mm bars at the bottom throughout and 216 mm bars throughout at the top, and stirrups from face of the wall to the face of the wall, two-legged 8 mm at 300 mm center to center. We have taken a cut section. So we have used 20 mm bars at the bottom. So two numbers 20 dia at the bottom. At the top hanger bars, two numbers of 16 pi, and the loop is the stirrup, which is two-legged 8 mm at 300 mm center to center. Now this is the design output, manual design output. Now let us see how we will make it in STAAD-Pro. There might be slight variation because a lot of calculation roundups will be there with manual compared to a software, and then like in a design wise, slightly the reinforcement bars might be varying. So we have used 20 dia bars, STAAD-Pro might have used a different one. So let us check. So coming to modeling this beam in the software, so we have the following steps which have to be followed. The first one is the job information, then followed by geometry, material property, member property, constants, supports, loads and combinations, analysis and design. So let us start. So initially I will just show you, just rush through the PPT and then let us start doing it in the software itself. Step one, so once we open a new job, we end up in a job information page. Okay, so where we'll be able to enter the job name, client, job number, revision, part, references, then where we are going to store the file, that is the directory, then engineer's name who is modeling, uh, Engineer's date will be defaultly the date when the file has been created. Then checker name is date, approver's name and detail date will automatically be entered. And apart from that, we have input with in the command prompt, so which is 79. The 79 represents uh, alphabets, numericals, space, special characters, everything. So in a line we can type 79 characters, and beyond that STAAD-Pro will not be able to read. And the other information which we need to feed initially is length and force units. Length units we normally take meters, and for force we use kilonewtons. So this information is more important, else by default, if it is in English system, then we have to revise it. Else if it is in metric, we are happy with that. Let us continue. Then step 2, geometry. So as we all know, it works out like a graph. So what we try to do is like we put the joints, or we call it as nodes. So for a beam we need two nodes, the start node and the end node. So this window shows the node information. So node numbers, x coordinate, y coordinate and z coordinate. X is along left to right, it is positive. Y is vertical axis, down to upward it is positive, and z is focusing towards us. So we are going to make in xy plane. So since we are making it as a 2D, so the plane which we are going to use it as xy. So node 1 and node 2. So node 1 is the initial node, I'm taking it as 0 0 0, and node 2 is 5 meters, that is the length of the beam. So x is 5, y is 0, and z is also 0. Then member incidences. So now we have defined two nodes, so we need to join them. So that is called as member incidences. So in this member incidences, so what we are going to see is like we are going to add a beam with start node and then end node. Now start node is always at the left, and end node we have to see that it is always at the right, so that we have clarity where we have placed, where we are placing the start node and where we are placing the end node. So now in this case, node 1 is the left and node 2 is the right. So we are defining here beam number is 1 and node A and node B, so 1 and 2. So with this we get a beam on the STAAD-Pro. So let us check where in the software, so whether we get it or not. Step 3, material property. So once we have defined the geometry, then we are defining the material property. So depending upon the grade of concrete, we are going to enter its properties like Young's modulus, Poisson's ratio, density, thermal coefficient, then critical damping, shear modulus, and the compressive strength of the concrete. So this information we need it. So by default, STAAD-Pro will have a few information, but depending upon the grade of concrete, we have to modify them slightly. Once that has been done, then we are going with the member property. Member property is nothing but the cross-sectional area. So we are going to give the cross section. YD represents the depth and ZD represents the width. So YD, we have calculated the overall depth of the beam as 450 mm. So we are taking it from the manual one. So overall depth is 450 mm. And width of the beam we have taken as 250 mm. So we are feeding it as 0.25 meters. And at the bottom, we are selecting the material. So that is the constant. So what is the step 5 constant represents is nothing but we have defined the material property separately and member property separately, but we have to tag them. So for example, I have a beam, it can be steel, it can be aluminum, it can be concrete, or it can be timber. So that constant defines like what material it is made of. So we are tagging concrete to the member property. So concrete property have been already defined. So those property will be added to this beam also. Then step 6, supports. Since we are using a simply supported beam, one end is pinned, so we have a predefined pin support. So we can pick it up from the software. And the right side support we normally give it as a roller. So for roller, we are using the command called fixed but. So we are releasing fx and mz. So these two forces are released to make it as a roller support. So this is the point which we need to remember. For roller, we are removing fx and we are releasing fx and mz, and then followed by loads. In loads, initially we define the load cases. So here I have given it as dead load, then load 2 as live load, then load 3 is combination 1.5 times dead load plus live load, and load 4 is 1 times dead load plus live load. So initially we have defined the load cases. Once load case has been defined, so for the under the dead load case, I'm adding the self weight. So self weight, I'm just adding it up as a self weight comment, global y minus 1. That is the factor is minus 1. So that is more than enough. Then for the live load, we had 10 kilonewton per meter. So that is added as a member load. So load which is going to act on a member is called as a member load. Under member load, I'm adding it as uniform force, that is UDL. So under that, I'm adding it as minus 10. So minus indicates gravity direction. So W1 is minus 10. And since the load is applied throughout the beam, so I'm not defining any D1, D2, D3. So default minus 10 means the 10 kilonewton per meter is applied throughout the length of the beam, and direction is GY. So we are not touching the direction part. Now same way, how to add a combination. So click on the combination, we get a tab like this, then give the name, and then give the load factor, then does it then pick the load cases with the multiplying factor. So we get the load combination. So in this case, it is 1.5 times dead load and 1.5 times live load. Step 8, analysis. Click on the analysis button, we get a window like this. So as of now, let it be no print. Let us run the analysis part. And then once analysis has been successfully run, then we go with the design part. So under design, we have a lot of parameters to be given. Then only we will get a result which is similar to that of the manual design. So under design, first what we do is like we pick up the code. So IS 456. So we are picking up. Under that, we are defining the clear cover, grade of concrete, grade of main bar, grade of main secondary bars, then maximum main bar, what is the diameter we are going to use, maximum secondary bars diameter. Then in case of bar combination, we have to give what is the first bar, what is the second bar, and then minimum main. Okay, so earlier we have defined the maximum main. Here in this case, we are going to define the minimum main, and then followed by minimum secondary. Then ratio is 4, the longitudinal steel percentage. Then spacing between the main bars we have to define. Then track 2 is for printing design results. Then uh, concrete take, so that will give us the beam design, then in beam design. Okay, so once we have done that, then we get the output. So uh, let us see how to model this in the STAAD-Pro software. Now I'm opening up the STAAD-Pro. It's starting with a new project. Clicking on let it be space. I'm defining it as SS beam, simply supported beam. Somewhere it is getting stored. Units, meter and kilonewtons. So this is the main one. Since we are working with the metric system, we are using meter and kilonewtons. Next, let it be add beam and finish it. Now, once we have given finish, we get a page like this, okay, with a grid. I'm just closing this grid so that we get the job information. Okay. Now, how the STAAD-Pro works is, this is the modeling area. On the right side, we get windows for uh, the comments. Okay, so for example, member property or metal property, geometry, everything we get the windows on the right side. On the top we have the tabs like file, edit, view, tools, geometry, comments, analysis mode, etc. And then we have the icons here like open, new, save, and then the views. Then we have the add beam, add plate, all those options over here. And then we have the zoom options, print options. Okay, and then we have the output options here, which is inactive now. And on the left tab we have the selection. So node, we have a node cursor, beams cursor we have separately, plate cursor, surface cursor, like this way it goes on. And then we have this modeling. This tab is more important. If we follow this tab, then we won't end up in any error. For example, setup is the job information. So by default I'm creating this file today, which is 19 May 2020. So default it has come. Okay, suppose I want to define some name, I'm just giving ssb, simply supported beam. And if I have any other information I can fill. Now as of now it is academics purpose, so we are not entering any information over here. And then followed by geometry. Now geometry, we have two different methods to enter. One is like this grid. Okay, so where we can set up this grid in the front view, so 1 to 10 meters. Or the easier one will be like close this, we get this uh, node information page and the member incidences page. So let us start here. I'm giving the node 1 as 000. Then node 2. So the beam length was 5 meters, effective length. So I'm just feeding it as 5. So I've got two nodes here on the screen. Okay, I'm just showing you shift N. So node 1 and node 2. Okay, so I need to connect these two. Okay, so I can just pick up from here, add beams option, then click on node 1, then click on node 2. So we have got it. Okay, you can see on the right side we have got this information, node 1, 2. Okay, beam 1, starting node is 1 and end node is 2. Okay, press shift B, so we'll be able to see the beam number. Okay, so we have defined the geometry part. Now next one, general. I'm just going this way, general. So we get this property page, member property. So since we are using concrete, I'm clicking on define. So rectangular section, so we'll be feeding the depth. So YT represents the depth, so which we have calculated as 450 mm and width was 250 mm. So I'm feeding YDS 0.45 meters and EZDS 0.25 meters, and material default it is concrete, let it be. Okay, now we have added a section. Now this section has to be assigned. So for that purpose we have four different assignment options. So at the bottom we have assign to selected beams, assign to edit list, assign using cursor, and then assign to view. Now let us go with assign using cursor. I'm clicking on. So first we have to see that this is the section which we have to assume. We have to provide is getting selected, highlighted, then click on assign. You will see that we are able to provide that. Now you see that the color change, R1 represents the reference section 1. So that section is 0.45 into 0.25. Okay, so we have defined the member property. Default material property has been linked. Slightly we have to modify those material property. Let us see how to do that. So once member property has been done, then we don't have any specifications in this, since it is a very simple beam. Then comes the support. So you can see that I'm on the left tab, I'm just moving. Initially was set up, then geometry, now general. Under general, I'm done with property, now with support. Now support, we get a window like this. So click on create. Fixed, pinned, or predefined supports. Now we'll give a pinned support. So this is uneditable. So pin, I'm adding it up. Then again click on create. we need a roller at the right end. So the option is fixed, but we have to release fx and mz. So that is nothing but along x direction we have a movement. We have a movement. So slightly it can slide, and mz has to be released. Okay, if not, it acts as a fixed support. Okay, so fx and mz are released to make it as a roller. I'm adding it up. Now let us use again the cursor to assign. So support 2 has been selected, and use cursor to assign. Click on node 1. Okay, then click on support uh, 3. Still it is in the assignment option only. I'm just directly clicking on the node 2. Okay, press escape. So I have assigned the pin support to the left end and the roller support to the right end. Let us close this. Now supports has been given. Then the next is loads and combinations. Now once I click on the loads window, I get a window like this. Okay. Now click on the load case details. Click add. Initially it is in the primary cases. So let it be load number. Let it be 1. I'm defining it as dead load. Okay. Since I want to know what I'm doing it there, so I'm just giving it as dead load DL add. Okay. So you can see that load case 1 dead load has been added. Then automatically it goes to the next load case number 2. I'm taking it as live load. Okay. Then I'm typing the title as live load LL, add it. Okay, I'm closing it up. Now click on this dead load. We are going to add the self height of the beam. Since the cross section has been defined and the metal properties have been defined, so we have to give the option of self height. Then the software itself will calculate the self height component. So click on dead load, then click add self height y direction -1. Okay, so by default it is there. So let us add it. Close. So whenever there's a red question mark, that means like we have to assign. So click on the self height. So self height we can give it as assign to view. So I'm using a different method here, assignment method, assign to view. Okay, done. Then click on the live load, add. Now we had a uniformly distributed load of 10 kilonewton per meter acting throughout the beam. So in STAAD-Pro, that kind of load is called as a member load. Okay, so let us click on member load. Member load is nothing but load is acting over a member. So in this case, it is uniformly distributed load. So that we call it as a uniform force. Okay, so uniform force is the default one. So uniform force, and then let us define the intensity. So -10. Minus represents the gravity direction. Okay, default we have gy, let it be. And this d1 and d2 we have to define if we have a partial udl. Okay, so in this case we are having the udl from start to end of the beam. So let us not define this d1 d2 and even d3. D3 means it is going to create a torsion. Now in our case we are assuming the load is acting on the CG of the beam. Okay, so let us add it. I have not added any other parameters. I've just added it. Now again, there's a question mark, so we have to assign. So in this case, I'm using assign to selected beams. So first select the load, then click on the beam. You can see that this option is active now. Assign to selected beams option is active. So click to select this assign to selected option. Then okay, so we have updated the loads. Fine. Now next is load combination. So to add a load combination, so click on this load cases, add, we get a window like this. So here click on define combinations. Okay, so name I'm giving it as 1.5 times dead load plus live load. Okay, and then the load factor is 1.5. Okay, I'm adding both the beam, both the load cases. So I get as like dead load into 1.5, load case 2, that is live load, into 1.5, add it. So we have got this load combination, 1.5 times load 1 and 1.5 times load 2. And then for deflection and serviceability limit state, we need one more load combination. So that is 1 time dead load plus live load. Okay, so factor is 1. I'm adding up these two. Okay, so dead 1 time and live load as 1 time. So I'm adding it up again. So now we have defined two combinations. One is for the serviceability limit state, where the partial load factor is 1, and the other combination is for ultimate limit state, which will be used for design. The partial load factor is 1.5. Okay, now we have defined the loads and load combinations. Let us go for analysis. Click on the analysis. Now I'll just pick it from the tab here. So click on the analysis. You can see like a window opens like this. Now let us add, simply add, done. I'm not clicking on anything else. I'm just adding it up. Once that has been done, okay. Now let us run the analysis. Analyze, run analysis. Okay, let us see if we have any error or not. So there is no errors, warnings, or notes to this one. So we are happy. Okay, let us check uh, the post processing mode. So I'm just going to the post processing window. Okay, now initially what we get is the displacement, and then we get the reaction. So it is under what is that, live load. So we know 10 kilonewton per meter acting over 5 meter span. So reaction at both ends will be 25 kilonewton. Okay, now same way you can find out the deflection. Okay, so press control and scroll, this image will increase. Okay, so on the right side we have this displacements. For example, live load. So we are seeing that live load 2.5 is the mid span. So the displacement at mid span is 1.963 mm. Okay, now let us go to beam to check uh, moment and shear force. So once we click on beam, we get the bending moment displayed. So this is moment about Z axis. So MZ is active. Okay, so this moment is what we use it for the design purposes. Now click on results, view value. I'm just clicking on the maximum. Okay, so I'm just picking up this ultimate. We have the value with us there. Okay, we have got 59.3 kilonewton meter, but we got slightly higher there, 60 point something. So we have to modify something. We will see what has to be modified. And same way we have this shear force, Fy. Okay, now this is the output one. Fx represents the torsion, or the, sorry, axial force. Then Fy is the shear along Y, then shear along Z, then torsion, then we have bending about Y, then we have bending about Z, then we have the stresses, then we have the deflection. Okay, and the final one is the mode shape. Now again we have the shear, uh, whatever the shear force we get it for a UDL, so we have obtained it. Now we have to slightly modify the material properties since we are using M30 grade concrete, so which has not been seen earlier. So just click on the STAAD editor, so just below the comments. I'm just clicking it on. Okay, so click on define materials on the left tab. Okay, so Young's modulus value of M30 grade concrete, so it is 27386. Okay, in e power 10 into e power 7. Okay, 27,386 kilonewtons. If you want to round up, you can make it. Okay, then Poisson's ratio 0.17, and then density of concrete, we assume it is 25. Default it is 23 point something, so that is the change. Now we will get that 61 kilonewton meter as bending moment. Okay, 60 point something will get, and then the ultimate compressive strength, so 30,000 kilonewton per meter square. Okay, so this is the change that we are making it up. uh, this change cannot be done graphically, so we are doing it on the editor board. So we have revised Young's modulus value, density of concrete, and strength of concrete. So three parameters we have revised. Save and close. Okay, now analyze it. Let's go to the post processing and check the bending. Okay, so I'm just going to the results, view value, maximum. Okay, I'm keeping the front view. So 60.059 kilonewton meter, that was the actual result. So for design purpose, we have rounded it to 61 kilonewton meter. Right. Now coming back to the design part. Now we have the shear force also. Let us check the shear. Fy is the shear component. So again, go to results, view value. Let us take it at the ends. We get the maximum shear at the ends. So 48.047. We have taken it as 49 kilonewton for the design purpose. Okay, so this is the actual result which we are getting. Okay, let's go to the modeling again. Now we will add a few comments for design. So go to design. Okay, click on concrete design. We get a window like this. Now select the code. We are going to use IS456. So I'm picking it up. So at the bottom, we have select parameters, define parameters, and comments. We'll start with define parameters. We are going to feed a few parameters which we are in need of. Clear is nothing but the clear cover. So we are defining it as 0.03, 30 mm. Add it. Okay. And then depth, let it be default. We are going to add this grade of concrete. Okay, so compressive strength of concrete, we are going to use 30, so 30,000 kilonewton per meter square. Add it. Yield strength of main reinforcement, so we are going to use 4 on 5, so I'm adding it as 4 on 5 000, converting it into kilonewton per meter square. Same way secondary steel, so again we are going to use it as 4 on 5 000. Add it. Okay, then maximum main, as of we are worried about only the minimum main, so let us not worry about this. Then minimum main, I'm just giving it a 16 mm for the longitudinal reinforcement and 8 mm for the secondary reinforcement. And then we are going to go with let us add a few more. Then the spacing between the bars, so 0.1, I'm adding it up. And then torsion design, we don't have any torsion force. I'm entering 2. This is for printing output, so that is need not be done. It need not be entered. Okay, then add comments, design beam, again add it, close. Hope I have added it. Right. Now we have a lot of question marks here, so those things have to be assigned. I'm just clicking on each one. I'll give it as assigned to view since we have only one beam here. Or we have assigned to edit list. I can give the beam number and it can be added. So I'm just adding using edit option. Okay, so this is done. Now let us run the analysis again. So we are not going to click on perform analysis. We are just going to run directly. Okay, so I'm just giving it a save. Let us see the output of the design. Okay, so double click. We have got the concrete here. Okay, now what it displays. Okay, so you can see the design load at the bottom. Moment 60.06. Okay, distance is at 2.5 and load case is 3. The load case 3 is nothing but the combination of dead load and live load multiplied by 1.5, and 2.5 meter is the mid span, and 61 we have taken here. In this case actually it is 60.06 kilonewton meter. Okay, so for this one it is designed. Okay, and on the right side design parameters are there. So Fy for main we have taken 415. Okay, FCK grade of concrete is 30, depth is 0.45 meters, width is 0.25 meters, and length of the beam is 5 meters. Now just check the longitudinal section of the elevation. Okay, so at the bottom we have got 316 throughout. Okay, and at the top we have 216 throat. Okay, now we have given 220 mm with the manual analysis at the bottom, but whereas STAAD-Pro is giving 316. Now because the software will start with the minimum bar and it will proceed on, so we don't want to have three number of bars, so we have given 220 mm. Now in this case STAAD-Pro is given as 316. Okay, at the top 216 continues, and stirrups it is giving it as 8 mm at 300 center to center. So number of legs you can see with the cross section. Okay, here it is giving the number of stirrups to be provided. So from the left end it is 8 numbers of 8 mm stirrups. From the right end it is 8 number of 8 mm stirrups. Okay, so this is the end of STAAD-Pro results. Now I'm going back to the presentation, so where I made the comparison. So I'm just clicking on the presentation. So let us see the results. Okay, so bending moment, the actual one without rounding up, we get a 60.059 kilonewton meter. So we get the same in STAAD-Pro. The bottom one is a STAAD-Pro result and top one is the manual one. Okay, and same with shear force, we get the same amount of shear force. Okay, so initially in STAAD-Pro we were not getting because the density of concrete was 23 point something. Then we have revised it to 25, so we are getting the same amount of shear force. Okay, and then the design part. Now we have provided 220 at the bottom and 216 at the top, and stirrups 8 mm at 300 mm center to center. So we are getting almost the same, except at the bottom STAAD-Pro is arranging 316 mm bars, so we are going with 216 mm bars. Now this variation is because STAAD-Pro will not do the combination of bars. Okay, so because of that, what happens is like it has taken 316 mm, since we have defined it as the least uh, main bar, so it has taken 16. So that's the only difference. Else we are getting almost the same. Okay, so 316 is 603 mm square, and 220 mm is 628 mm square. Okay, so that is the only variation. So even might be we could have arranged it 360, since we have taken it as 220, so that is the variation. Okay, if we go with 20 bar in the STAAD-Pro software, then at the top also we will get 20 bar. So that is the difficulty. Okay, so with this, the session on STAAD-Pro, design of a singly reinforced beam, comes to an end. Comments are welcome. Thank you.